In 1976, Nobel laureate Felix Bloch gave a talk to the American Physical Society to commemorate the 50th anniversary of the publication of Schrödinger's equation. Here is the story he told. When I entered the Swiss Federal Institute of Technology in my hometown of Zurich, I began as a student of engineering. But after a year and a good deal of soul-searching, I decided against all good sense to switch over to the entirely useless field of physics. I had started to attend the physics colloquium regularly, although most of what I heard there was far above my head. Once at the end of a colloquium, I heard Peter Debye say something like, "Schrödinger, you're not working now on very important problems anyway. Why don't you tell us sometime about that thesis of de Broglie that seems to have attracted some attention?" So, in one of the next colloquia, Schrödinger gave a beautifully clear account of how de Broglie associated a wave with a particle and how he could attain the quantization rules of Niels Bohr by demanding that an integer number of waves be fitted along a stationary orbit. When he had finished, Debye casually remarked that he thought this way of thinking was rather childish. To deal properly with waves, one had to have a wave equation. It sounded quite trivial and did not seem to make a great impression, but Schrödinger evidently thought a bit more about the idea afterwards. Just a few weeks later, he gave another talk in colloquium where he started by saying, "My colleague Debye has suggested that one should have a wave equation. Well, I have found one." 50 years on from that talk of Felix Bloch, we are now at the 100th anniversary of Schrödinger's discovery. So today, let's follow in Schrödinger's footsteps to see how he came up with his famous wave equation. Welcome to Atomic Universe. I'm Dan Bergstrom, material scientist. Following in the footsteps of Schrödinger's two colloquium talks, this video also has two parts. I'll start with a quick review of de Broglie's electron wave theory, including a review of the particle-wave duality theories of light that preceded it. Then I will go through the Schrödinger wave equation, how he derived it, and how he applied it to calculate the electron energy levels for the hydrogen atom. To start our discussion of particle-wave duality, we should really start with Maxwell's equations. In the 1860s, James Maxwell pulled together Gauss's laws on the electric and magnetic fields, Faraday's law of magnetic induction, and Ampere's law of electromagnetism into a unified description of vibrations occurring in electromagnetic fields. To see how these equations work, let's apply these laws to the example of a radio antenna. To create radio waves, an alternating current is sent through a wire. By the first part of Ampere's law, the current J will create a magnetic field B whose strength is the current times a constant for the magnetic permeability of space, mu naught. The upside-down delta with a cross is a vector operation called the curl, which means the magnetic field will spiral around clockwise when the current is flowing away and counterclockwise when the current is flowing towards the viewer. Since this magnetic field is changing with time, it again creates an electric field by Faraday's law, which is equal to the rate of change of the magnetic field. This changing electric field, in turn, creates a new magnetic field by the second half of Ampere's law. This time, the magnetic field strength goes as the product of the magnetic constant and the electric permittivity constant, epsilon naught, times the rate of change of the electric field E. This feedback between the magnetic and electric fields continues, generating an electromagnetic traveling wave. To calculate the equation of motion as wave involves a bit of vector algebra, which I won't go through in detail. But the bottom line is when you combine Maxwell's equations, you find that the sum of the second derivatives of the magnetic field with respect to each of the spatial dimensions, a quantity known as the Laplacian, is equal to mu naught times epsilon naught times the second derivative of the magnetic field with respect to time. In the last episode on wave equations, we went through the derivation of a generic equation for a traveling wave. There, we found that the second derivative of the wave displacement with respect to time equals wave velocity squared times the second derivative of displacement with respect to distance. If we rewrite our equation this way and solve for velocity of our electromagnetic waves, we get v equal to 1 divided by the square root of mu naught times epsilon naught. When we plug in the known values of these constants, lo and behold, we get the answer that these electromagnetic waves are traveling away from our moving charge at the speed of light. These equations then were essentially how Maxwell proved, beyond a shadow of a doubt, that light was really just electromagnetic waves moving through space. By the end of the 1800s, no one in the scientific community seriously doubted that light was a wave. In 1905, however, a patent clerk in Bern, Switzerland dared to say otherwise. Albert Einstein was to write a number of groundbreaking papers that year on atomic theory, special relativity, and his famous equation E equals mc squared. But his first paper that year was on his particle theory of light. Einstein wrote that energy during the propagation of a ray of light is not continuously distributed over steadily increasing spaces, but consists of a finite number of energy quanta localized at points in space, moving without dividing and capable of being absorbed or generated only as entities. The concept of light with quantized energy was a mathematical trick that Max Planck had used to fit the spectral intensities of light emitted by hot objects. The minimum amount of light energy possible was Planck's constant times the frequency of the light. Einstein said this was not just a trick, it was a feature of light that it traveled only in particle-like packets, what we call photons today. With this viewpoint, he could quantitatively explain phenomenon like the photoelectric effect, where light particles hitting the surface of a piece of metal can kick out electrons. The energy of these light particles was again given by Planck's constant times the frequency, a proportionality that is now called the Planck-Einstein equation. With this formula, we can move back and forth between thinking of light as a particle with a certain energy or as a wave with a certain frequency, the so-called particle-wave duality. Although Einstein's work on the photoelectric effect won him the 1921 Nobel Prize for Physics, not everyone was convinced yet that light was really particle-like. But in 1923, an experiment by Arthur Compton at Washington University in St. Louis would prove once and for all that Einstein was right. Compton reasoned that if light was a particle, then it should carry momentum. In Compton's experiment, photons of X-ray light were scattered off electrons then remeasured. He noted that the frequency of light was lower after scattering, and using conservation of momentum, he could calculate the momentum difference of light before and after the scattering. The relation he found from these experiments said that the momentum of light particles was equal to Planck's constant divided by the wavelength. If photons had momentum and could kick electrons around just like billiard balls, they must be particles. But what about electrons? Everyone knew that electrons were particles, but also there was something funny about the way electrons orbited the nucleus in the atom. Orbiting electrons, essentially an oscillating charge, should generate electromagnetic waves, as we have seen. Conservation of energy said the electrons therefore must slow down and spiral into the nucleus. Classical physics was clear: the atom could not be stable. In 1913, Niels Bohr came up with an answer. Picking up on Planck's mathematical trick, Bohr assumed that the orbital momentum of the electron was quantized to be an integral multiple of Planck's constant divided by 2 pi. This set a sort of a bottom floor for the electron orbit where it could not go around any slower. Using this quantization, Bohr calculated the electron energies associated with each possible electron momentum and found that the difference between these energy levels for the hydrogen atom precisely matched the energy of photons in the hydrogen emission spectrum. This meant that electrons could only generate electromagnetic radiation by moving between the quantized energy levels that Bohr had calculated. But why were electron momenta quantized in this way? No one knew. The math just worked. Now at last we come to Louis de Broglie's PhD thesis of 1924. De Broglie made a radical proposal that the electron was both a particle and a wave, just like the photon. And furthermore, by reversing the formula Compton used, de Broglie calculated the wavelength of the electron as Planck's constant divided by the electron's momentum. What really made de Broglie's thesis exciting was that he used the wave-like nature of the electron to explain the riddle of Bohr's quantized energy levels of the atom. Now, those of you that saw the last episode on wave equations will remember that when we looked at standing wave vibrations on a loop of string, quantization emerged naturally from the boundary conditions that the string be continuous. The loop could only support standing wave vibrations where whole numbers of wavelengths fit along the length of the string. De Broglie made the same argument. An electron orbiting an atom could only take on whole numbers of electron wavelengths along the circumference of the orbital path. That circumference is 2 pi times the radius of the orbit, so it must be equal to n times the wavelength. Plugging in Planck's constant over momentum for the wavelength and rearranging gives us that the angular momentum must equal n times Planck's constant divided by 2 pi, exactly the formula that Bohr had previously calculated. So at this point, we're up to speed on the key details Erwin Schrödinger would likely have presented in his summary of de Broglie's thesis in the fall of 1925. Now let's try to understand Pierre Debye's objection that de Broglie's analysis was childish. Again, going back to that equation for the standing wave on a loop of string, those of you who saw the last episode will recall we were able to derive it from a second-order differential equation of motion applying Newton's law of F equals ma to the mass elements in the string. The sinusoidal standing wave vibration was shown to be a solution of the equation which satisfied the continuity constraints of a string looped back on itself. Debye's objection was that jumping to a sine wave solution for the electron wave function said nothing about the underlying physics. The gold standard for using wave equations to understand physics was Maxwell's equations. Maxwell calculated proper wave equations based on the underlying physics, which then allowed the speed of light to be derived. Compared to Maxwell's brilliant analysis there, de Broglie's approach was indeed childish, insightful, but not fully worked out. Inspired by Debye, during the winter break at the end of 1925, Schrödinger got to work, putting some meat on the bones of the electron wave theory. In our last episode, we saw that for a snapshot in time, a wave on a string will have the second partial derivative of the wave displacement u with respect to distance x equal to minus the square of a frequency factor omega times the displacement u. This is where Schrödinger started his analysis, although he used the variable psi to indicate the wave function instead of our displacement u. Since omega is defined as 2 pi over the wavelength, we can plug that in, along with de Broglie's equation for the electron wavelength, and the definition of momentum as mass times velocity, to get the electron's equation of motion as the second partial derivative of psi with respect to x equals the quantity 2 pi times mass times velocity divided by Planck's constant, all squared, times the wave function psi. To clean this equation up a bit, we can make two substitutions. We can define the constant h bar as h over 2 pi, and we recognize from basic physics that we can take 1/2 the mass times the velocity squared and call that the kinetic energy of the electron, Ke. The final step is to say the total energy of the electron will be its kinetic energy plus any potential energy, which we'll call V. Thus, we can plug in E minus V for Ke and move all the terms to the left side to get the final equation as the second partial derivative of the wave function psi plus twice the mass divided by h bar squared times the total energy minus the potential energy times psi equals 0. And voila, we have arrived at Schrödinger's equation. Of course, this is only the one-dimensional Schrödinger equation, but we can easily extend it to higher dimensions by adding terms for all three directions, the second partial derivatives of psi with respect to x, y, and z. Again, this is the Laplacian operator, which we can abbreviate using an upside-down delta squared pronounced as del squared. So del squared of psi plus twice the mass divided by h bar squared times the quantity, the total energy minus the potential energy, times psi equals 0. And this is the formula you will most often see in textbooks as the time-independent Schrödinger equation. The first problem that Schrödinger himself tackled with this equation was to fix up de Broglie's childish model of the hydrogen atom and generate a proper three-dimensional wave function solution for the electron orbitals. In this problem, the potential energy is the Coulomb potential of the proton that comprises the nucleus. This potential is equal to the unit charge E squared divided by 4 pi epsilon naught r. To solve the wave equation for drumhead vibrations in the last episode, we converted the Laplacian operator to polar coordinates and solved for the radial and circular vibration modes separately and then combined them. Schrödinger took a similar approach. Since the atomic potential is spherically symmetric, it makes sense to solve this equation by using the Laplacian for spherical coordinates and solving separately for the radial and angular vibration modes. One thing to note here is that in polar coordinates the angle theta represents rotation in the xy plane, but in spherical coordinates, confusingly, theta is now the azimuthal angle measured down from the z-axis, and phi represents the rotation in the xy plane. Let's now assume that our wave function equals the product of independent radial and angular vibration modes, which we'll call capital R and capital Y. Since these are independent, the derivatives of R with respect to the angles are 0 and vice versa. Next, we separate out the angular terms and replace them in the original equation with an arbitrary constant, -c. Now we have two equations. The first describes the radial vibration modes, and the second describes only the spherical vibration modes. The latitudinal and longitudinal vibration modes of a sphere were studied by Pierre-Simon Laplace himself and collectively are known as spherical harmonics. Again, by analogy to the drumhead vibrations in the previous episode, you can think of the spherical harmonic modes as vibration modes for a soap bubble. Just as the drumhead had standing wave vibrations quantized with integer variables, the vibrations on a surface of a soap bubble are quantized by the integers L and M with modes as shown here. The equation for the vibration modes is abbreviated as the function y subscript L superscript M, which is a function of theta and phi as shown. L is any non-negative integer, which includes 0, and M can be any integer in the range from negative L to L, which results in a total of 2L plus 1 possible values of M for every possible L. A more common way to plot these spherical harmonics is to make contour plots on the surface of a sphere where the intensity of the vibration is indicated by the contour colors. To more clearly see the nodes of zero vibration, I've drawn them as black circles. Note that the total number of nodes is given by L, and the number of nodal planes running through the poles along longitudinal lines is given by M. The remaining L minus M lines, which lie along the latitude lines, correspond in 3 dimensions to cone-shaped nodes of zero vibration at fixed angles from the z-axis. So now you have a good sense of the spherical harmonics, but what of the solutions to the wave function in the radial direction? Well, we'll need to use a special function here analogous to the Bessel functions we used in the last episode to solve the two-dimensional Laplacian. The solutions we need are called the generalized Laguerre polynomials, symbolized with a capital L, from the French mathematician Edmond Laguerre. The details of these equations are not really important, but I'll plot them so you can see what they look like. Laguerre polynomials are a series whose increasing order is quantized by an integer, I'll use the subscript k, that represents the number of zeros for the function. The generalized Laguerre polynomial has another parameter, superscript alpha, which has the effect of stretching the function towards larger radii. Due to the atomic potential being a function of the radius, our radial vibration will get weaker at larger radius, so our final radial solution will be the Laguerre polynomial times 2 exponential terms shown here, which will ensure that our vibrations taper off to 0 at infinity. In these terms, the radius is normalized by dividing by the Bohr radius A0, which represents the radius of the lowest energy electron orbit. They're also a function of n, which is the principal quantum number and represents the total number of nodes for the system where there is zero vibration. Since there will be L total spherical nodes, plus the one at infinite radius, there will be n minus L minus 1 total radial nodes, resulting from our Laguerre polynomial. So k equals n minus L minus 1. Since k cannot be negative, this puts an upper bound on L that it cannot be more than n minus 1. Since more spherical harmonic modes mean a lower density of radial nodes, the waves in the radial direction can be spaced further out. It turns out that the alpha of our Laguerre polynomial will be equal to 2L plus 1. There also needs to be a rather complicated normalization factor for our radial function that ensures that our vibrations will only represent 1 electron worth of energy. Putting all this together, we can now plot the product of all these terms, which shows you the radial distribution function of these electron waves. Here I chose L equals 0 solutions for various values of n. We can also animate these with a time factor so you can see how the zeros represent nodes of zero vibration. These nodes form spherical shells in 3 dimensions, and we can visualize these in 2 dimensions by using intensity maps of vibration modes in the same way we looked at drumhead vibrations in the last episode. These are contour plots of the square of the time average of the radial wave function. Yellow is where the vibration is the most intense, and the dark blue areas represent nodes of zero vibration. The reason we are plotting the square of the wave function is due to German physicist Max Born. He interpreted the square of the wave function at any given location as the probability of finding the electron there during any experiments which treat the electron as a particle. So with that interpretation, these contour plots have a secondary meaning as probability contours. Each color represents different odds the electron will be found there. The electron's likely to be found in yellow regions and unlikely to be found in the blue regions. So if we now go back and combine the radial and spherical harmonic functions, we have our full, rather complicated, solution for the 3-dimensional electron wave function in the hydrogen atom. These solutions are quantized by the integers n, l, and m, subject to the constraint that n is greater than 0, l is less than or equal to n minus 1, and m is in the range bounded by minus l to l. The next challenge for us is to actually visualize these wave functions in 3 dimensions. Let's try to plot, as an example, an orbital with n equals 4, l equals 2, m equals 1. We'll want to use a Laguerre polynomial of order n minus l minus 1, which means it'll have one zero vibration node. It will be multiplied by an exponential factor involving minus r, which goes to 0 as r gets very large, and a factor involving r raised to the l power. If l equals 0, that term becomes 1, but for any l greater than 0, this will give us another 0 for the function at r equals 0. The normalization factor is just a scaling factor, and that doesn't change the location of the nodes. Putting these all together then, for our example of n equals 4, l equals 2, our radial distribution plot will have 3 nodes, one from each of the 3 factors involving the radius. Here is a 2D contour plot of the square of the radial distribution function as we plotted before. The spherical harmonic function we need for our example is l equals 2, m equals 1. Here is the spherical contour plot from the square of that function. If we take a slice through the interesting part of the sphere and multiply it by the radial distribution function, you can see a 2D slice of the final electron orbital. It's not always easy to plot these functions in 2 dimensions, however. If we repeat this process with the example of n equals 5, l equals 3, m equals 2, we get a very similar 2D plot. But if we look at the spherical harmonic contour, we see that the plane that we chose to cut it missed some features above and below the plane. We can try to extend our 2-dimensional contour plots to 3 dimensions by assembling the 2D contour plots for planes normal to each of the x, y, and z axes. And as we rotate this view in 3 dimensions, you can clearly see the difference between these 2 orbitals. The more common way to plot electron energy shells is to pick a particular contour level and plot that contour as a 3-dimensional shell. These are the 3D plots that you'll often see in textbooks, and they show the volume inside which the electron is very likely to be found most of the time. For me, I think that superimposing these 2 kinds of plots gives the best feel of what the orbitals really look like. Let's look at 3 different orbitals now, all with n equals 4. The first has l and m both equal to 0, so all the nodes are spherical shells. The second maxes out l at 3, but keeps m equal to 0. Here there are 3 azimuthal cone-shaped nodes. Well, the middle one's actually the xy plane, but we can call that an honorary cone in spherical coordinates. The third orbital maxes out l and m at 3, and you can see all 3 nodal planes now intersect the z-axis. To each of these orbitals, we need to add a 4th node, which is due to the wave function going to 0 at infinite radius. So as we said before, all wave functions will have n total nodes of 0 electron probability, in this case 4. The number of nodal planes which intersect the z-axis will always be given by m, and there'll always be l minus m conical shaped nodes. It is worth it to take a moment to reflect one last time on the example of standing wave vibrations on the string that we reviewed in the last episode. As n increased, the number of nodes increased, and so did the vibrational energy due to the higher frequency harmonics being played. Similarly, the vibrational energy of an electron wave function increases with the total number of nodes. For a hydrogen atom, then, the total electron energy can be calculated as a function of the principal quantum number n. In fact, when Schrödinger did this calculation, he was able to derive the same equation for electron energy that Bohr had determined empirically. The energy for an electron wave function with quantum number n, or E sub n, is equal to about negative 13.6 electron volts divided by n squared. This negative number is the energy which is binding the electron to the atom. As n increases, the vibrational energy of the electron is greater, and the binding energy to the nucleus is correspondingly lower. This agreement with Bohr's result and the spectral energy data behind it was a major confirmation of the validity of Schrödinger's equation. So that's about it for the case of one electron in the hydrogen atom. In future episodes, we'll look at more complicated atoms and atomic bonds, but for today, let's just close by looking at the beauty that is the full set of hydrogen wave functions. At n equals 1, we have one solution, and this is called the 1s orbital. At n equals 2, we have 4 solutions, the 2s orbital and 3 different 2p orbitals, which each have one planar node along the planes normal to each axis. At n equals 3, there are now 9 solutions, representing each of the possible configurations of 2 nodes chosen from the different types, plus the nodal shell that's always there at infinity. The bottom row here are called the 3d orbitals. At n equals 4, the orbitals are becoming very intricate. If you look down the central axis, you can see how the azimuthal nodes replace the radial nodes as you move down. And as you move from the center outward, you can see how the vertical planar nodes replace the azimuthal nodes. There are 16 n equals 4 solutions, including 7 different solutions for the L equals 3 4f orbitals. At n equals 5, I think these orbitals have become truly fascinating. I could stare at these all day. These electrons are only bound to the nucleus by little more than half an electron volt, so now it is increasingly likely to find electrons orbiting several nanometers away from that tiny proton in the middle. We could go on forever, but n equals 5 seems like a good place to call it a day. I do hope you've enjoyed celebrating the 100th anniversary of Schrodinger's equation with me. Thanks for watching.